Yeah. Okay, so in the last class we spoke about um, how stability or equilibrium happens when two non-interacting gases mix. And we deduced that when there are two non-reacting gases mix, there will be no change in their enthalpy. The enthalpy contribution will be zero. And that's one of the reasons that they don't react, means there's no heat exchange involved. There's no heat evolution or absorption of heat. But then two gases mix up instantly, spontaneously. That means the system goes for a change in free energy, goes to a lower free energy. The Gibbs energy change is negative. And since Gibbs energy is a combination of the enthalpy contribution and entropy contributions, and enthalpy contributions being zero, therefore the mixing is actually facilitated by the change in entropy. So what happens is when two gases mix, they, the first gas is now, before mixing was really limited to its own volume. Now when you mix, it is open to the total volume, and likewise the other component of the gas, the gas B, that also has the whole volume to fill up, so as to randomize the distribution, and that enhances entropy. And the negative term of that is actually with temperature. The negative term with the temperature is actually what is giving you reduced free energy, reduced Gibbs energy of the system, and that's why it's spontaneous. All right. Um, this one will come to it, where how you change pressure with fugacity. We'll take it up at some other time. Now, consider a situation where um, two gases mix, and at one point they also react. And here I want you to look at two examples where nitrogen gas mixes with argon gas, and eventually what it forms is nothing. It's simply a mixture of nitrogen and argon. Nitrogen was contained in a volume, and argon is contained in a separate volume. Now, when they are mixed, uh, what happens is nitrogen and argon both are contained to the combined volume. And even in this process, like we discussed, there'll be change in free energy that's going to be negative, and this is going to be a spontaneous process. All right. But then, since these two gases do not react with each other, this enthalpy contribution is zero. Okay, because it's not a reaction at all. But then, what happens when there are two gases? They react, and a random example is, for example, like hydrogen reacts with oxygen and forms water. And what would happen? How would you assess the change in free energy, change in Gibbs energy? But that before that, how do you assess the stability of the system? Um, what would be the eventual composition of the whole system, the combined system? And how would you define equilibrium when there is a reaction going on? And what do I mean by how do you define a system at equilibrium? It might so happen that you start with hydrogen and oxygen, and consider that the conditions are right for the reaction to happen. Then it will form water. But then would it be equilibrium when these two gases completely react and form water, and the end of the system is complete water? Like the beginning of the system was completely hydrogen and oxygen, end of the system is completely water. Does it happen? Turns out it doesn't happen unless you control the reaction. If you let the closed reaction to an equilibrium, it might so happen that some hydrogen would react with some oxygen, of course stoichiometrically, and form water. But in the middle of the system, there'll be some hydrogen and oxygen would still be left, and some water would be formed. And completion of the reaction would not be possible. Would not happen unless, of course, you change subtle things. And then the question that therefore is, how do you define the equilibrium composition? When is it equilibrium? What are those compositions where some amount of hydrogen is there, some amount of oxygen is there, some amount of water is there, and that's the most stable state. All right. And this is because there is a reaction. I mean, if there were no reaction, then you just simply say that it's the maximizing the mixing process or the randomness of the occupancy of the gas molecules throughout the volume. That would define equilibrium. But here, in addition to that, there's a reaction term involved, and then we need to see how it's happening. Okay. Now, we'll see in generic terms. Let's say gas A reacts with gas B and forms gas 2C, 2C moles of gas. So this is the stoichiometry, and this is a generic one. This we can put instead of A some numbers, some kind of gases depending on what the reaction is, and this is a generic one, right? Now, what do we need to do is find out the total energy of the system, right? Total energy of the system, total Gibbs energy of the system. How do you do that? It's simple, some Na is the number of moles of gas A that's available in the system at some instance that you're interested, and Nb is the number of moles of B gas available, and Nc is the number of moles of the C gas available in the system. And if you need to find out the total Gibbs energy system, you simply need to multiply Na multiplied by the partial molar free energy of component A. Likewise, you add it up. It's summation of Ni/Gi. That's the total Gibbs energy of the system. Now, if you want to find out the equilibrium, what you need to do is actually normalize, differentiate G with change in Na. That's the change that's happening, because more and more gas A and gas B are reacting to form gas C. So the change of this free energy with a change in the composition Na, or any N for that matter, and that equated to 0 would actually give you the mathematical combination of finding a reaction equilibrium. All right. So like if you go to this reaction here, what is happening is 1 mole of A is reacting with 1 mole of B is producing 2 moles of C. All right. So this is very important for to look at, because here it's kind of a balanced equation in the sense that 2 moles of reactant gases are producing 2 moles of product gases. All right. If you change this ratio, then there'll be subtle changes that we'll eventually look at it. But then for that matter, initially, let's say 1 mole of A and 1 mole of B are reacting to form 2 moles of C. And if we start with the equimolar combination of A and B, then equal moles of A and the same moles of B would react to form double the moles of C. That's what's written here. Say if we say that Na moles are reacting or Na moles are available, then Nb is the same thing, because you start with the stoichiometric composition, and then A and B are equimolar here in the reaction phase. All right. So Na is Nb, and Nc is therefore 2 minus Na minus Nb. So you'll form Nc, and you can find out the number of moles of C, because C is formed only with half of A and half of B. That means 1 part A and 1 part B gives 2 parts of C. So the point is that at any instance, the total number of moles in the system is always 2, because A and B are disappearing and then C is forming with a ratio, of course. And the ratio is such that the total number of moles in the gaseous mixture in the middle of the reaction also is going to be 2. And that's what's written here. This is Na is Nb and Nc is 2 minus 2Na. That's 2 into 1 minus Na, because Na is equal to Nb. So therefore, you can define all of the number of moles that is available with all different gases in terms of Na. So therefore, G is going to be Na Ga and NaGb bar, and then 2 into 1 minus NaGc bar. All right. And this is a generic formula. The GI is GI 0, which is the standard unmixed state, and this is in the mixture. All right. And this is RTLNP, RTLNXI. These are true comes, and this comes because here GI 0 plus RTLN small p I. That's the formula, and then small pi is nothing but the total pressure into mole fraction, and this is in a generic form. And we expand the same thing for A, B, and C. They're going to look like this. Now, it's also important to define the mole fraction. All right, and the mole fraction is Na by 2 because this is the number of moles available for the component A, gas component A, normalized by the total number of moles that's available in the system. If you add up Na plus Na plus 2 minus 2 Na. Okay, so every instance starting from A plus B to complete C, everywhere the number of moles that is present is 2. That's why it's normalized by 2. That's what is giving you mole fraction. Xa is Na by 2, and likewise Xb is Nb by 2, which is Na by 2 itself, and Xc is, you normalize this by 2 again, is 1 minus Na. Right. Now, based on these information, we can actually expand this quantity G, right? And here is a long one, but I don't need to go to the derivation of it. You can actually do it yourself. But I'll bring your attention to these couple of lines here. You get an expanded line like this. And let's say if we enforce another condition that we are doing the process, we are doing the reaction in a total pressure of 1 atmosphere. Let's say, for example, right? We can change that to a different atmosphere. That it's not going to make much of a difference. But for simplicity, let's say we are doing the reaction at P is 1 atmosphere. So this term actually goes away. So what you're left with is here, G is a combination of a couple of terms, okay, right? Or whatever is there, we can actually split it up into two parts. One is 1 minus Na into del G0 plus 2 RT, and this expression which is Na ln Na by 2 plus 1 minus Na ln 1 minus Na, right? So the point I'm saying here is that this total energy actually is a combination of something which is related to the Gibbs free energy of formation of the compound C, or the component C. And there's another term which actually talks about mixing of all of the gases that is available. Right? Now, before the reaction, we talked about gaseous mixtures where despite not having a reaction, the gases still spontaneously mix. That's because they want to maximize their entropy. All right. So that situation is always going to be here. But then, because there's a reaction, there's a reaction free energy as well. Okay. And del G is actually corresponds to that. All right. And I can tell you this. So this is the example where, and this is the line. Okay, and this is one more line, and these are the lines that are given. And what we are saying is that this is the curve 1 is the total energy curve. Curve 1 is the total energy curve. We'll come to this a little later, a little more detail. But then this one is the total free energy, and curve 2 is the enthalpy of the reaction. Okay, you can call enthalpy of the reaction. You can also call Gibbs energy of the reaction. Right? Why do you say that? Because there's a difference. Because enthalpy doesn't talk about the entropic part, but when you talk about Gibbs free energy, it also includes the entropic contribution as well. So, okay, I'll come to that. And again, you have curve 3, where the curve 3 is because of the free energy of mixing. All right. So what I showed in the last equation is that this curve actually is a combination of this curve as well as this curve. All right. If you look at it, it's these two curves are added to give the curve 1. Right. Curve 1 is a summation of curve 3 and line 2. Right. Now let's go a little deeper, going back to the previous slide. I say this is del G zero, that is gives energy of reaction, and here I write enthalpy of reaction. Is it wrong? Perhaps it is wrong in the normal sense, but then it's not wrong here. Why is that? Because enthalpy and Gibbs energy of the system are fairly equivalent. Why is that? Why do you say that? Because you need to understand that there are two kinds of um, uh, entropy contributions involved here. All right? Entropy contributions meaning if you look at this reaction, here gases are mixing to produce a gas. So by the reaction itself, would there be a major change in entropy? Perhaps not. Because when major change in entropy happens because of the reaction, okay, that happens when, let's say, a liquid becomes vapor. That's a major change in entropy. When a solid becomes a liquid, there is still a positive change in entropy, but then not as significant as an entropy change would be from liquid to vapor state. All right. So that reaction also is embedded, when you talk about Gibbs energy of the reaction and enthalpy of the reaction, there could be subtle differences. All right. There's one thing is the um, because there's a phase change, and the phase change actually involves a major change there in their absolute entropies. But then when you talk about gases form a reacting to produce another gas, what kind of what is the extent of entropy change that you can expect? Fairly minimal. All right. So and again, because the reactions are between two or multiple gases are reacting to form another gas, so the change in entropy is rather minimal. On top of that, let's say we particularly when we talk about this reaction here, 2 moles of gases are reacting to form 2 moles of gases. Although the gases are different because this A and B are reacting to produce another gas which is C, but then eventually if you look at the number of moles that is available before the reaction or after the reaction, it's the same number of moles. So the point I want to bring up is that free energy change or entropy change can be of two types as well. Because first is the reaction type, because the nature of products that are forming from the nature of reactants that might involve either increase in entropy or decrease in entropy. That's point one, which is something which is contained here itself, and that's why we call it Gibbs energy of reaction, right? But when you talk about enthalpy of reaction, you just simply talk about the heat is either evolved or absorbed, all right? But here we should not worry too much about that because the entropic contribution of the reaction itself is not so significant. So it is enthalpy or Gibbs energy, it's pretty much the same. Okay, but then the other part of the reaction, other part of the entropy form is this one, because here eventually you had A and B only, and from the spontaneity of processes when A and B do not react even, and you know that even after not reacting, A and B immediately mix up to form a mixture, and that's a spontaneous change. That means Gibbs energy is reduced. That means entropy is increasing in the system. Now we are talking about a situation where A and B first mix among themselves to produce a mixture of A and B, and then they react to form something like C. All right. So you have, instead of 2 components, you have 3 components already available. Now, when those 3 components are available, and the whole volume is there for them to sort of occupy space, entropy is going to even more increase even more. So this part actually talks about that randomization, that statistical distribution of the A and B and C gas molecules throughout a space, and how best can you disperse entropy or disperse energy from that distribution. That is something which is increasing entropy. All right. So here is a combination of the enthalpic part or the Gibbs energy part, and this is a combination of the entropy part, and which is what is given here. And if you look at it, it is 1 minus Na del G. If you look at Gaskell's book, it is slightly confusing. I have changed the sort of derivation and the nomenclature slightly. Gaskell writes this as G prime, and then instead of 1 minus Na del G, it writes Na del G. All right, but I thought the proper form would be 1 minus Na del G. Del G 0. Why is that? Let's look at it. If you look at this line, right, and this corresponds to Na, where here is 1, it is completely 1, all right. So this is the total number of gas molecules A and B are available for reaction. And when you go into this phase of reaction proceeds in the reaction coordinate, we say that Na is gradually decreasing. What does it mean? That means A and B are disappearing from the system. And what is forming? C is forming. So that's what's happening here. Na is coming down and C is increasing as a double of this. Right? So this is 1, it's coming down to 0, and this is 0, which is coming down to 2. More and more of these things are formed. All right. So if you look at this, if you say multiply Na into del G, that's going to be wrong. If you multiply 1 minus Na to del G, that'll be useful, because if Na is available is 1, 1 minus 1 is 0. So at this point, this is 0. The Gibbs energy of formation part is 0 here. But as you move in the reaction coordinate, that means if you proceed the reaction to the right, that means more and more and A and B are reacting to form more and more C, then this line is actually increasing. Increasing meaning increasing in the negative direction, because perhaps the reaction that we are talking about is an exothermic reaction, right? That's a del G or del H is negative, and since there is no effect of del S, del G therefore is negative. All right, so that's one of the reasons that this curve is coming down here. All right, but when you talk about the mixing part, right, when you talk about the mixing part here, even before A and B reacted to form C, A and B were mixed together. All right, let's see that. Let's see that here. Something is given here from the book. It's at 500 Kelvin for the reaction that we're talking about. Let's say that del G0 is minus 5,000 joules. This is just a number, which is corresponding to this diagram. Right now, at the beginning of the reaction, let's say A and B are a mixture and there's no C is formed, then at this point, let's talk about L to M. L to M, A and B would be mixed. Okay, and A and B would be mixed in what proportion? Then proportion of 1:1. And what will be the free energy change in a gaseous mixture, not considering any reaction, but then just the mixture itself? 1:1 would be written as, Ni RT ln Pi by capital Pi, which is the total pressure. That is simply as RT Na ln Pa by Pa, and Nb ln small pb by pb, which is actually half and half. Okay, that eventually gives you the del G L to M is minus 5,763 joules. Okay, and this is only because of the mixing of A and B. There's no reaction already involved here, right? And if you go back to this one, if you see that this is 5,763 in the minus, that's L to M, and that has formed without any reaction. That's only because of A and B mixing together, which is the first part of the discussions we had, for the gaseous mixing. And from here onwards, reaction starts as well as the mixing. Okay, and how do you deal with that? We can go back to the optimizing the energy for equilibrium. And there's a simple strategy. I don't want to make it more complicated. This slide will give you the eventually more important thing to consider is let's say when we take the total energy, we can find out the total energy of the mixture at generic stage, at any stage. We find out the total free energy, and we differentiate that to a changing of the number of moles of any component, and you equate that to 0, and this G, as you know, is Na Ga bar with NaGb bar and 2 into this number of moles of Gc, and you multiply that with Gc bar, and these are the partial molar free energies in the mixed state. And there is something called a Gibbs-Duhem equation. We'll deal with that later, which says that if it is G is the combination of the summation of Ni mu I. G is a combination of Ni mu I. But when you do dG, then it's going to be a combination of mu dNi plus N d mu. Mu dN plus N d mu. And this Gibbs-Duhem equation says that the N d mu part is actually 0. All right. So when you differentiate that, you can simply, neglect the N part, and at constant temperature pressure, del G by del Na is something which is the partial molar free energy of Ga plus partial molar free energy of Gb minus partial molar free energy of twice of Gc. That is equal to 0. And the criteria for equilibrium then, therefore, simply reduces to this form, which is the partial molar free energies of component A and component B, these are the reactant phases, is equal to the partial molar free energy of the product phase. That's what the reaction condition is, right? And that's where the equilibrium would be attained. That means these are the chemical potentials of the reactants and chemical potential of the products that balance out. Okay, and therefore the reaction would not proceed further, neither in the forward direction nor in the backward directions. And that's going to be stale. Okay, and that's why the stale is equilibrium. That it'll try to maintain equilibrium at that point. All right. So we can actually expand onto these numbers and then figure out what eventually would be our expression for equilibrium. All right. So if we say that G, a partial molar free energy of A plus B is equal to twice of the partial molar free energy of C, then we can expand onto these things in terms of the standard free energies standard pure free energies in the unmixed state of A as well as B as well as C, right? And this, is GA0 plus RTL and PA, that's the partial pressure of A, and GB0 plus RTL and PB, that's partial pressure of B, and like this one is also in the partial pressure of C, all right? And now if you rearrange some of these things, you'll find that this is products minus the reactants standard free energy, that is minus RTLN PC square by PA PB, and this term would differ depending on the number of constants that you have, coefficients that you have, and in a generic way you can put it by putting an X and Y depending on the reactions that happens, right? And this is nothing but del G0, which is the standard free energy change for the reaction, and this we define as something called the equilibrium constant. I think you might be aware of that. This equilibrium constant, that is Kp, and you can simply write as del G. That is the most important form of chemical reactions. It's del G is minus RTL and Kp, and this is minus RTL and PC square by PABP, and you can calculate ln Kp because del G is given as 5000 minus 5000, and again this del G put 5000, and RT talking about at 500 Kelvin, you can find out that logarithm of Kp is 1.2 and then Kp is 3.329. That's just an example of the numbers that is given in this problem. Now, and then because you know Kp now, can you find out what's the equilibrium composition? I think that'll be easy. Okay, and this Kp is what? Pc square by PAPB. All right, now you have Pc, Pa and Pb, and you convert that to the number of moles of gases available, and likewise you can find out the mole fraction in the system, right? The mole fraction is xc square by p square and xap by xap and xbp, which is simply turning out to be xc square by xaxb. Pc square by PAPB is xc square by xaxb. That is 3.329. And then you solve this one, right? Because you know what is XA XA and XB, because you have this Na and 2 into 1 minus Na, and based on that you can solve and find out Na is 0.523. Here a word of caution is that always this Pc square by Pa Pb is not going to be Xc square by Xa Xb. This is happening here because these P's cancel out, and these P's cancel out because two moles are reacting to form 2 moles of products. Okay, if there is an imbalance, all right, if more moles are reacting to produce less moles, or less moles are reacting to produce more moles of products, then you cannot simply convert the partial pressures to mole fractions, right? There has to be a term of P involved here. When we do additional examples, then we'll be able to figure it out. So I hope you're clear that Na is 0.523 now. And what does it mean? That means the reaction equilibrium happens at Na is equal to 0.523 and Nb is equal to 0.523. And that would mean Nc is equal to 1 minus 0.523 multiplied by 2. That is 0.954. Okay? Or in another way, you could say that A plus B is 2C has proceeded to 47.7% of the reaction completion, and that's where equilibrium happens. All right, so that it's going to be kind of clear here. So this one, it doesn't talk about the mixing process. It just simply scales with more and more amounts of NC formed or C formed. That means when more and more C are being formed, it simply multiplies that with the del G of del G is the standard change in free energy for the reaction, and it simply keeps on increasing. More C is formed, larger negativism, because the reaction itself is negative energy, so more and more it becomes. So exactly at the completion of the reaction, it's going to be 5,000 joules, because that's what is written, and then at 500 Kelvin, the del G of the process is minus 5,000. So this is minus 5,000, right? And talk about curve 3. This is what it does is it's the immediate mixing of A and B without any reaction or without any C being involved here. It brings down to something, or what was the number? Minus 5763 or something. It's come here. And after that, it starts mixing up with B and C into the thing. So here it's at this point. At this point is where it's maximizing, or it's the lowest energy contribution from the mixing process. All right. So but then the eventual free energy, which defines the stability of the system, is which defines the stability of the system is actually a combination of this and this and this, isn't it? So you add up these two, you see that the equilibrium then, because of this contribution, the equilibrium shifts slightly to the right, and this is the point S is the eventual equilibrium, where we say that the 40 we figured it out. The Na is 0.523. This is Na is from here is 0.5, that's 0.523. That's what it is. That means it has proceeded about 47 odd percentage from the start of reaction, which is mixture of A plus B. It has come to 47%, and that's where the reaction is at equilibrium. And what does it mean? That means some amount of A and B are there, along with some amount of formed C, and this is what is giving you the reaction equilibrium. All right, so this is what it is. We'll talk about subsequent things in the next lectures. If there are questions, I'll take it now. So let me stop the recording and we'll talk.